In Chapter 11, we're initially going to take a step back from intermolecular forces and look at the interactions between ions in a crystal structure. So it's kind of like what you may have learned in previous classes, the ionic bond, but we're going to be looking at the energy of that bond and what affects how strong that bond is. And then we'll look at vapor pressure again, similar to last chapter, but in this case we'll be looking at vapor pressure of mixtures rather than the vapor pressure of pure liquids. And at the end, we'll relate that back to intermolecular forces. Okay, so last chapter we learned about intermolecular forces, which are the attractive forces holding particles together in the liquid or the solid phases. And they result from Coulombic attractions, so the partial positive and partial negative charges that are present on each of these molecules. And the strength of those interactions is dependent on the magnitude of the charge, as well as the distance between each of those charges. So for example, on this HCl molecule, we would have a slightly negative charge by the chlorine and a slightly positive charge by the hydrogen. And the bigger those partial positive and partial negative charges, the stronger the interaction will be between any two given molecules. So the intermolecular forces that we learned about in the last chapter are all weaker than the interactions we're going to be learning about in the first part of chapter 11 here, because those were only partial charges, so less than 1. Whereas for ions, we're going to be dealing with full charges. So for example, sodium has a +1 charge, calcium has a +2 charge, fluorine has a -1 charge, and oxygen has a -2 charge. So these are all full charges, which are going to result in stronger interactions than what we had or what we learned about in the previous chapter. So ion-ion interactions are dependent on a couple of different criteria. The first being the actual charge on the ions themselves, and those are represented by Q1 and Q2. So Q1 being the charge on the first ion and Q2 being the charge on the second ion. The other criteria that's going to determine the strength of these interactions is the distance between the two ions. And this is going to be represented in terms of distance in picometers. Picometers meaning 10 to the -12 meters, so quite a small distance. And the attractive force is going to increase as the charges increase. So a +1, -1 ionic combination is going to be a weaker charge than a +2, -2 ionic combination. And as the ions are closer together, they will have a stronger interaction than if they were farther apart. So on this slide, we have a partial periodic table that shows the different sizes of anions and cations, as well as different atoms. So I'm going to zoom up to look at a couple of different cations here. So we'll look at lithium, sodium, and potassium. So notice that as we go down the periodic table, as we would expect from lithium to sodium to potassium, the atom itself increases in size. That's because we have a greater number of electron shells, which makes the atom bigger. Now, if we look at the ion, so the ion of lithium, lithium +1, is smaller than the atom of lithium. Sodium ion, sodium plus, is smaller than the atom, and potassium is smaller than the atom. And the reason for that, of course, is that a positive ion has fewer electrons, in this case one fewer electron than its respective atom. So each of those electrons is going to feel an additional force pulling it towards the nucleus of the atom, thereby making the atom itself smaller. And if we look at +2 ions, so we got beryllium, magnesium, and calcium, for example, notice that the +2 ion is smaller than the +1 ion that's right beside it. So for example, beryllium 2+, which has the same number of outer electron shells as lithium, but the ion itself is smaller than lithium. again, because it's lost now 2 electrons, being a +2 ion, so each of those electrons again feels a greater force towards the center of the nucleus, resulting in a smaller ion. So beryllium is smaller than lithium, magnesium 2+ smaller than sodium plus, and calcium 2+ smaller than potassium. So for positive ions, the ion itself is smaller than its respective atom. If we look over here to fluorine, chlorine, and beryllium, for example, also oxygen, sulfur, and selenium, we can see that the negative ions end up being larger than their respective atoms, right? So here's the atom, here is the ion. And the reason for that is since each of those ions has a negative charge, that means that additional electrons have been added to the atom to make the ion, and adding additional electrons results in a larger size because each of those electrons now feels less of a force pulling it towards the nucleus. The -1 ion for fluorine, for example, is a little bit smaller than the -2 ion for oxygen. Okay, oxygen has, it's a -2, it's added an additional electron, so it should be a little bit bigger. Now, the one thing I didn't mention yet was what these numbers are. So the 73 and the 140 for oxygen, the 71 and the 133 for fluorine. That is the radius of the atom on top or the ion on the bottom. So the numbers that you'll be using for the calculations that you have to do are going to be the numbers for the ion. Okay, so for example, fluorine 133, chlorine 181, and again, those values are in picometers. Okay, this slide just shows you some sizes of polyatomic ions. So these polyatomic ions we will run into throughout the course of the term, not necessarily in this context, but in, like, for example, acid-base context. But this is just showing you that there are, the size differences between different polyatomic ions, starting from carbonate on top, nitrate is the next one, sulfate, and phosphate. Okay, so let's just go through a quick example and get an idea of how you would have to think your way through one of these types of problems. So predict which salt in the following pairs exhibits the greater ion-ion interactions. So what are the two things that you have to think about? Well, if we go back to our equation that we saw previously, we know that the energy or the strength of the force between two ions is going to be proportional to the charges on the ions. Greater the charge, the stronger that interaction. And it's going to be also dependent on the distance between the ions. The farther apart those ions are, the weaker that interaction is going to be. So if we just look at this intuitively first, we can do the calculation on the next slide to see if our intuition is right. So we look at magnesium oxide. Okay, if you go back to the couple slides ago, the partial periodic table, look up magnesium, look up oxygen. Notice that they both have 2's in the charges, so magnesium +2, oxygen -2. And if you look at sodium and fluorine, you would notice that sodium has a +1 and fluorine has a -1. So initially it seems like the charge is going to have some kind of an effect, right? So we have a larger charge with the magnesium and the oxygen in comparison to the sodium and the fluorine. So because of that, we might expect that magnesium oxide should have a stronger interaction. And if you look at the distances, there's not a lot of difference between the distance. So it seems like the charge is probably going to have the biggest effect. So you might think, based on no calculation at all, magnesium oxide is going to have the strongest interaction. Okay, we'll look at that in a second just to see if we're right. And we'll just check out B intuitively. So magnesium oxide and magnesium sulfide. The magnesium is the same, so that's not going to have any effect on the strength or the difference in the strength between those two salts. The only difference being the oxygen and the sulfur. Okay, both magnesium, oxygen, and sulfur have either +2 or -2 charges. So the charge isn't going to have an effect. So the only effect that's going to determine the strength of this interaction is going to be the distance between the ions. So you look at the distance between the magnesium and oxygen and the distance between the magnesium and the sulfur. And you notice that the distance between magnesium and sulfur is larger, so that should result in a weaker interaction. So we'll take a look at the math in the next couple slides, and see if our prediction is right. Okay, so what we have here is, we'll start off with A. So we have our equation, right? So Q on top is the charges, D is the distance. So for the distance between the ions, you'd just be adding up the radius of each of the ions involved. So for example, we have our calculation for magnesium oxide. So we have magnesium 2 plus and oxygen 2 minus on the top of the equation, and on the bottom the distance between the two ions, represented by the radius of magnesium plus the radius of the oxygen. Magnesium has a +2 charge, oxygen has a -2 charge. The radius of magnesium is 72 picometers, the radius of oxygen is 140. And if you solve that equation, you get that number there. Do the same thing for sodium fluoride. Okay, sodium fluoride, sodium with a +1, fluoride with a -1. Radius of sodium 102 picometers, radius of fluorine 133 picometers, and the result of that calculation is that number there. So how do you interpret those numbers? Basically, you look at the one that has the largest negative number, and that is going to be the one that has the strongest interaction. So our intuition from the previous slide, or our previous discussion for what we would expect to be the strongest interaction, ends up being true if we go through the math, because we have a larger negative number here in comparison to that one there. Now if we look at magnesium oxide and magnesium sulfide, okay, remember magnesium is the same on both of them. They both have +2 or -2 charges, so this part of the equation for both magnesium oxide and magnesium sulfide is going to be the same. The radius of magnesium is going to be the same in both of them. The only difference is going to be right there, the radius of oxygen versus the radius of sulfur. Okay, so we would expect again that since the radius of sulfur is larger than oxygen, that should be a weaker interaction. So this is the same number that we got in our previous calculation, the previous slide. This is what we get for magnesium sulfide, and notice that that is a smaller negative number, which fits our prediction. For this next section, there's actually not a lot that I'm expecting you to know. Your book goes into a whole bunch of processes called the Born-Haber process, and I'm not going to be worried about that kind of thing. So mainly what I'm worried about in this section is to know what lattice energy is, and I'll explain that on the next slide, and just to understand a little bit about some of the energies involved in that crystal, and say what happens when that crystal of, say, sodium chloride in this example. So if this was a sodium chloride crystal, what energies are involved in that dissolving in water? Right, so this diagram here is showing first that we have a lattice energy, which is the energy that is associated with that crystal itself, the energy that is holding each of those ions together. Okay, so we have that energy there, and so what has to happen? Well, those bonds have to break. Okay, so the energy to break those bonds is going to be part of the process of the crystal dissolving. So how much energy is that? And since it's in water, we have water molecules here, and each of those has hydrogen bonds between them. And in order for the water to dissolve the crystal, those hydrogen bonds have to break, because those individual water molecules are going to have to interact with the crystal lattice structure, or each of the ions, in an ion dipole interaction, as we learned about last chapter. And then there's also going to be the energy involved in each of those ions creating a solvation sphere, or each of the water molecules creating a solvation sphere around each of the ions. So adding all those energies together is going to be the energy that is required to dissolve the crystal. So the lattice energy is actually defined as the energy released when 1 mole of the solid ionic compound forms from its free ions in the gas phase. So that's represented by this chemical equation here. So it's showing M as some metal, X usually means a halide, such as a bromine or a chlorine or a fluorine. So for example, in this case, our M might be sodium, our X might be chlorine. So those ions in the gas phase forming a sodium chloride crystal, that energy involved in that process is called the lattice energy. And the equation to determine what lattice energy is, if you look at it, looks very similar to the equation that we've already seen. A couple differences is that this is definitely an equal sign, so the number that we get out of this would be an actual energy. And then there's also a constant, a K in there, which is dependent on the actual crystal structure of the ionic compound that we are interested in. So just as a quick comparison of lattice energies, okay, so we have a table here on the left which shows lithium fluoride, lithium chloride, and so on. And on the right, the numbers associated with each of those ionic compounds is in kilojoules per mole. Right, so this is now a measurement. It's now has some kind of a value associated with it that means something. And we can use the criteria and the thinking that we used for the practice problem to explain why each of these compounds has its respective lattice energies. So as before, the lattice energy is going to be dependent on the charge of the ion as well as the distance between the ions. Okay, so if we just zoom up on this table, look at lithium fluoride, for example. So lithium has a +1 charge, fluorine has a -1 charge, but they are both really small ions, so they should have a relatively strong interaction. Now, if you compare that to lithium chloride, so the only thing changing between lithium chloride and lithium fluoride is of course the chlorine. Chlorine is bigger than fluorine, so we should have a weaker interaction, and you can see that we do have a weaker interaction. Again, the larger the negative number here means that we have a stronger interaction. Okay, so if we go to sodium chloride, we have a bigger cation in sodium, and the chlorine is the same here. Okay, so the sodium is different. It's bigger, so we should have an even weaker interaction, and we do, compared to lithium chloride. And the next comparison, potassium is bigger than sodium. Again, we still have the chlorine, so since the distance between the potassium chloride is greater than the distance between sodium and chlorine, we have yet a weaker interaction, and we can use the same argument to argue about why potassium bromide would have a weaker interaction than potassium chloride. And I'll let you try and figure that one out yourself. If you have any questions, of course, you can ask. Now, the difference between the last two, magnesiums have a +2 charge, and the oxygen and magnesium oxide has a -2 charge, whereas the chlorines have a -1 charge. So the big jump in energy that you see here, or even from lithium fluoride to magnesium chloride, has to do with the +2 charge on the magnesium. And maybe it's a little bit more directly comparable to, say, lithium chloride or sodium potassium chlorides. Okay, it's still quite a bit larger number. And then magnesium oxide is another jump because we have a -2 charge on the oxygen. So that's about all I need you to know about the lattice energy. And so next we're going to be moving on to vapor pressures of solutions. And I just like to mention that the animated video for this particular chapter goes into this in some pretty good detail. So you might want to use that as a reference as well as what I'm going to be saying here. So when we're talking about vapor pressures of solutions, we can say in general that the vapor pressure of that solution is going to be lower than the vapor pressure of the pure solvent. So for example, if we have a container that contains pure water on one side, seawater on the other, what will happen over time is that the water will evaporate faster than the seawater because it has a greater vapor pressure than the seawater, which is a solution of salt and water. And what will happen is that the seawater side will end up increasing in volume, whereas the water side will end up decreasing in volume. And that's because the rate of evaporation of the seawater side is actually lower than the rate of condensation. Okay, so the seawater side still does have a vapor pressure. There is still some evaporation happening, but it's not happening as quickly as the pure water side. So that's why the water ends up in the right-hand side of the container rather than staying on the left-hand side. So if we wanted to actually calculate the vapor pressure of a solution, we'd use what's called Raoult's law. And what it states is that the vapor pressure of a solution is proportional to the mole fraction of the solvent. And we'll talk a little bit later on the next slide actually about what mole fraction is. And we're also going to be talking, at least in this section until we get to 11.4, we're going to be referring to a non-volatile solute. So a solute that does not evaporate, something like sodium chloride. So in this equation, the pressure of the solution, so for example, if we have a sodium chloride dissolved in water, sodium chloride solution, the pressure of that solution, the vapor pressure of that solution, is going to be related to the mole fraction of the solvent. And again, we'll talk about that in the next slide. And the pressure of the pure solvent, so the pressure of pure water. So that's what this little guy refers to here, P naught, right? So pressure P naught refers to the pressure of the pure solvent. Okay, and later in section 11.5, we'll check out vapor pressure lowering. And at the end of this section, we'll talk about ideal versus non-ideal solutions. But just for now, I'm just going to say that we're going to be assuming that this is an ideal solution. That probably won't make sense right now, but when we get to the end, hopefully that will. So let's just talk about a couple of concentration units. Okay, so molarity, hopefully you are familiar with, just the moles of solute per volume of solution. So if we have a sodium chloride solution, the moles of the solute would be the moles of the sodium chloride, and the volume of the solution is just simply the volume. Now, mole fraction is something you haven't seen before, at least I don't think you have, and it is the relationship between, for example, the moles of the solute. So again, if we have sodium chloride in water, that's going to be the moles of sodium chloride divided by the total moles of everything. So the moles of sodium chloride plus the moles of water. So what it's telling you is how many of the, or what proportion of the total moles in solution are from sodium chloride. And you could also do the same thing with water. You can replace moles of solute with moles of solvent to figure out the mole fraction of water, which is actually what is in the Raoult's law equation. Okay, so we'll go over an example a little bit later to check this out. Okay, but that example is going to be more in relation to mixtures of volatile solutes. So in this case, we're going to be talking about a mixture of, say, water and ethanol, where both ethanol and water can evaporate. Now, what we can do with these particular properties, or these particular solutions that are composed of two volatile components, or more than two, is to take advantage of the fact that each of the different solutes have different vapor pressures. So if we have an ethanol and water solution, water has a lower vapor pressure than ethanol, so we can use that property to help us separate the ethanol from the water, and that's a process called fractional distillation. Now, the video that I put up, the animated video, does have a fairly detailed explanation for how this works, but I'll just briefly go over it here. So I'm going to zoom into this fractional distillation column here, and I'm going to draw along these dotted lines little plates. So this is sort of what it would look like if you had an actual fractionating column. And what happens is we have, say, in this little flask at the bottom, so in this guy here we might have some ethanol and water. Ethanol and water there. And then we're going to heat it up using our heating plate there. So since ethanol has a lower boiling point or a higher vapor pressure than water, if this composition was, say, 50% ethanol and 50% water, so that's in the solution itself, that's in the liquid, but as it evaporates, so it's evaporating up here, that composition is going to end up being different in the vapor phase because more of the ethanol will be evaporating compared to water because it has a lower boiling point or a higher vapor pressure. So let's just say somewhere here in the vapor phase we have just for the sake of argument, a 60% ethanol solution and a 40% water solution. Now, as the vapor travels up to this first plate here, that vapor is now going to condense on that first plate. And the composition of the composition of the condensed vapor is going to be the same as the composition of the vapor. So this will again now be 60% ethanol and 40% water. Right? So now as the apparatus heats up, then this is going to evaporate from the first plate and it's going to condense on the second plate here. And just like the first time it evaporated, the composition of the vapor is going to be different than the composition of the what was condensed on that first plate. So say now we have a composition that's, just to make the numbers easy, we'll say we have 70% ethanol here and 30% water. Because this vapor, the vapor right here is going to maybe have that composition, and then when it condenses on the second plate, it's going to have the same composition as the vapor. So hopefully you can see the pattern here as we go up the column, or as the vapor travels up that column, it's becoming more enriched in the component that has the highest vapor pressure. So ideally what would happen is as we reach the end of the distillation apparatus, or the fractional distillation apparatus, ideally in here we have ethanol, and what we have left mostly on this side here is water. Okay, that's the ideal situation. Now the more of these little plates that we have, the more of these guys in here that we have, the greater the purity of our final product is going to be. Okay, so the next slide just takes you through that process in a little different way. So this graph here on the left is showing in red, that is the composition of the vapor, and the blue line there is showing the composition of the solution. So I'll just zoom into this part here, which is a zoom in of the graph itself. So you can read along in the slides. And so initially we're starting with a 50-50 composition of heptane and octane. And if you see, let me just scroll over there. Right, the boiling point of heptane is lower than the boiling point of octane, which would mean that heptane has a higher vapor pressure than octane. So when a solution of heptane and octane is brought to its boiling point, the vapor will have a higher concentration of heptane in it than it will octane. So this little graph here is showing you, the dotted line that you could also see on the large graph. This one here is showing you the composition of the solution, right? So this point represents the liquid because it's blue. So a 50-50 mixture, and when it boils, it has, the liquid has a composition of 50-50, but this over here to the left is showing what the composition would be of the vapor. Okay, so I'll just go over to the graph here. So that, what I just drew was here, and that is showing you now that the composition started at 50-50, but now the vapor has a composition of whatever that might be, say 35% octane and 65% heptane, just to make the numbers easy. Okay, so now as that composition, so this is the composition of the liquid that would condense on, say, that first plate that we saw on the previous slide. So now as that heats up and starts to boil, the composition is going to become even more enriched in heptane. Okay, so I'll go over here again. That's this guy here. So it became more enriched in heptane. So before we had 35-65, now it looks like we have 20% octane and 80% heptane. And if we take that one step further, again, this is the same composition in the liquid that condenses on the second plate now. And then as that comes to its boiling point, the composition of that vapor and the resulting condensed mixture is going to be, I don't know, you call that 8 and 92, for example. So 8% octane, 92% heptane. So if we continue this on and are able to evaporate and condense this mixture, eventually we'll get to a point where we have a very pure heptane solution, and it will have been separated from the octane. So that's the process of fractional distillation. Okay, so for mixtures containing more than one volatile compound, again, like ethanol and water or heptane and octane, in order to calculate the vapor pressure of that solution, we need to know the pressures or the partial pressures of each of the components within that solution. So if it were an octane-heptane solution, we would need to know the partial pressure of octane and add that to the partial pressure of heptane. And the partial pressures are going to depend on how much of each of those components is in the solution. So if there is a lot of octane and a little bit of heptane, the vapor pressure will more closely represent the vapor pressure of octane. If we have a 50-50 mixture, it's not necessarily going to be halfway in between the two vapor pressures, but it'll be somewhere in the middle. And if we have a composition of solution that is mostly heptane, then the total vapor pressure is going to be more close to the vapor pressure of heptane by itself. So the equation that we see here is very similar to what we saw before when we were talking about non-volatile components. So the pressure of the solution, or the total pressure of the solution, is going to be related to the mole fraction of component 1 times the vapor pressure of pure component 1 plus the mole fraction of component 2 times the vapor pressure of pure component 2, and so on and so forth. So we're just adding the partial pressures together, and the partial pressures of each component is being calculated by determining the mole fraction of each of the components and multiplying it by the vapor pressure of the pure component. Okay, so let's just go through an example of how you might do that calculation. So in this question, we're asked to find the vapor pressure of a solution of water and ethanol. And we're given the mass of water in the solution, the molar mass of water, the mass of ethanol in the solution, the molar mass of ethanol, and the pressures of the vapor pressures of the pure components. So we're going to be using this information to try and determine what the vapor pressure would be of this particular mixture. Okay, so how are we going to approach this problem? Well, first of all, we will be using the equation Raoult's law that we saw in the previous slide for mixtures of solutions. So we'll have the total pressure is going to be the mole fraction of component 1 times the vapor pressure of component 1 plus the mole fraction of component 2 times the vapor pressure of pure component 2. So what we have already in the question, we are given this information here, and we're given that information there. So this is the vapor pressure of pure water. This is the vapor pressure of pure ethanol. So what we need to find is the mole fraction of each of the components. So remember, mole fraction of component 1 is going to equal the moles of component 1 divided by the total moles of component 1 plus component 2. So in order to figure out mole fraction, we're going to need to find the moles, both of component 1 and component 2. And then we're also going to have to figure out what the total number of moles of everything is. So let's start off with ethanol. We'll start off by figuring out the moles of ethanol. Okay, so we are given a mass of ethanol of 25 grams, 25.00 grams of ethanol, and to convert that to moles, we have a molar mass, and the molar mass is 44 grams per mole. And if we do the math, we end up getting 0.5682 moles of ethanol. Okay, now we also need the moles of water. Okay, same type of calculation. We have 100 grams of water, and then the molar mass of water is 18 grams per mole, and then that's going to give us a moles of water of 5.556 moles of water. Okay, so now we have the top part, or the numerator of the mole fraction, and we now should determine what the total moles are so we can deal with the bottom half of that equation. So total moles is just going to be adding them together, total moles of solution, right? So that's simply going to equal the sum of each of the two moles of ethanol and water, and then we end up getting 6.124 moles. So there's our total moles. Okay, so now we're ready to figure out what the mole fractions are. So we'll start off with the mole fraction of ethanol, and that's going to be the moles of ethanol, which is 0.5682 moles, divided by the total number of moles of everything, 6.124 moles, and that ends up giving us a mole fraction of 0.09278. Okay, no units for mole fraction. And there are two ways to figure out the mole fraction of water. Either we can run through the same calculation, or we can realize that the mole fraction of different components all have to equal 1. So the easiest way to do this, to figure out the mole fraction of water, is to just subtract the number of moles, or the mole fraction of ethanol, from 1. So because the 1 represents the mole fraction of everything, 100% of all the moles, mole fraction of 1. 1 minus 0.09278, and that's going to give us a mole fraction of water of 0.9072. So now we have enough information to figure out what the pressure, or the vapor pressure of the solution is. So we're going to use Raoult's law as we have written above. So the pressure of the solution, or the vapor pressure of the solution, is going to be the mole fraction of ethanol, 0.09278. That's going to be multiplied by the the vapor pressure of pure ethanol, which is 57.8 torr. And then we're going to add to that the mole fraction of water multiplied by the vapor pressure of pure water, 23.8 torr. Okay, so if we run through that math, we end up getting a vapor pressure of solution of 26.95, or if we got this, the correct number of significant figures, 27.0 torr. Okay, so now notice that the vapor pressure of the solution is closer to the vapor pressure of water than it is to the vapor pressure of ethanol, right? The vapor pressure of pure ethanol, 57.8, the vapor pressure of pure water, 23.8 torr, and our answer being 27. So the vapor pressure is closer to water in this case because the solution contains a greater proportion of water than it does ethanol. So this is a good check when you're doing this kind of calculation on the homework or an exam. If you have more of one component in solution, then there's a good chance that the vapor pressure of the solution will be closer to the vapor pressure of the pure component. That is in the greatest proportion. Okay, so hopefully that all made sense. And the last thing that we're going to talk about is what I was talking about a bit earlier, ideal versus non-ideal solutions. So basically an ideal solution, it means that vapor pressures, when you have a solution, you can basically add up the two partial pressures, so the pressure of or the expected partial pressure of ethanol, for example, and the expected partial pressure of water, add them together, and you would get the total pressure of the solution. Okay, so depending on the composition of the ethanol in the water is going to give you a slightly different vapor pressure, right? If you have pure ethanol, it's going to be about 58. If you have pure water, it's going to be about 24 torr, and somewhere in the middle, depending on your composition, it's going to be somewhere between those two numbers. More ethanol is going to be closer to ethanol vapor pressure. More water in solution is going to be closer to water. Okay, so I just want to zoom up here and highlight the dotted lines here. Okay, so here's one dotted line. I'll make it black. Here's another dotted line. I'll make it black. Okay, so what this is showing you is the vapor pressures of component 1 and component 2, or component X and Y in this case. So if everything worked in an ideal world, then what you would expect for if you had, say, component A, so if you have 0% component A and 100% component B, so component B represented by this line, we'll call it component X just to match it up with the graph here, and we'll call this component Y. If you have, again, 0% component Y and all component X, the vapor pressure is going to be whatever the vapor pressure of component X is. Okay, so that number there. Now, as you increase the vapor pressure of component Y, or increase the composition of a component Y, the composition of component B is going to decrease. And ideally, if you add up this number here and this number here, what you end up with is this number here, so along this straight line. Okay, so an ideal solution means that you can add up, or you can calculate what these particular vapor pressures are going to be. You add them up, and they end up what you expect them to be. So if you added up those numbers, that's what you would get. Now, unfortunately, most solutions aren't ideal, and what that means is that we get graphs that look more like what you see here in color. So that the vapor pressures don't increase or decrease as expected because of the types of intermolecular forces that are present in the solution. So if I just zoom out here a little bit, you can see what those deviations are. So the first graph on the left represents a negative deviation from what we would expect if it was an ideal solution. So negative deviation meaning we expect a higher vapor pressure than what we actually observe. So the observed vapor pressures are what we see in the solid lines. The theoretical or expected vapor pressure are what you would see, or what we see with the dotted lines. So if we have intermolecular forces that are, some attractive forces between the solute and the solvent, so we'll use ethanol and water as the example. So our solute, say, is ethanol, our solvent is water. So if those interactions are stronger than the interactions between the solvent itself, then this is the kind of deviation from Raoult's law that we see. Okay, because the solute and the solvent, because their interactions are greater, they kind of want to stay together. So it's going to take a little bit more energy to actually get them into the vapor phase. So we would expect to have, just let me draw a point here. We would expect to have this much vapor pressure, but because the interactions between the solvent and the solute, the interactions between the water and the ethanol are stronger than expected, we actually only see that vapor pressure. So there's actually less in the vapor phase than we would expect because of the interaction between the solvent and the solute. Now, a positive deviation occurs when the solute-solvent interaction is weaker than we expect. So it's actually easier to separate the solute and the solvent than we would expect from a theoretical value here. Okay, so solute-solvent interactions are weaker than solvent-to-solvent interactions. So the solvent kind of likes to stay together, and it kind of, in a way, not really, but it sort of kicks out the solute. And since it's not, the interaction between the solvent and the solute is weaker, then more of that solute is going to be in the vapor phase than we expect. So as with the previous example, if this is what we expect, that particular amount of vapor pressure at that composition, we expect a vapor pressure of whatever that number is here. Because the interaction between the solvent and the solute is weaker than we expect, we actually end up getting a vapor pressure that's a little bit higher. So there's a little bit more of the molecules in the gas phase than we expect. Okay, so that's about all I have for these sections of the chapter, 11.1 to 11.4. And I think the next section, we will start talking about colligative properties.